In this exercise, we're going to be using modeling temperature in order to highlight the difference between an average rate of change and an instantaneous rate of change. So as you can see here in this exercise, we have that during a month, the temperature of the water in a pond is modeled by this given function, T of n, where n is the number of days after the beginning of the month, and T is the temperature measured in degrees Celsius. However, you can see in the questions that we first started by asking for the average rate of change in temperature during the first 18 days of the month, while the exact value of the instantaneous rate of change on day 18 is asked in part C. So this exercise will really help us highlight the difference. But before we start solving the exercise, we're going to just discuss in general the difference between the two. So an average rate of change is usually calculated over a period of time. So over here, if I were to start by sketching, just considering a sketch of a function, so considering the 2 points on the curve between A and B, the average rate of change between A and B would in fact be given by the slope of the segment that is joining these 2 points, because the average rate of change is the change in y divided by the change of x, which is in fact the slope of that segment. So the average rate of change would be the change in y divided by the change in x, which in this case, if I were to be calling this function f of x, so that would be f of b minus f of a over b minus a. So as you can see that the average rate of change is in fact happening over a period of time between two given points, and the average rate of change would actually be the slope of the segment joining these 2 points on the curve. However, for the instantaneous rate of change at a specific value, now that is a little bit different. So if I were to consider this function here, and I need to determine the instantaneous rate of change at x equals to a. So in this case, the instantaneous rate of change, since I want it at a specific instant, so this is where the word instantaneous come from, that it comes from the word instant, because I'm looking for the rate of change at a specific value and not over a period of time, similarly to the average rate of change. So at that specific instant, over here, it's like studying the rate of change at that margin, exactly at that value. So if I were to really consider a very small increment, so I would not really go further away from A. So if I were to really consider a very small increment, and then in that case, determine the average rate of change between these two infinitely close values. The average rate of change in that case being the slope of the segment joining them, you'd notice that because these two values are extremely small, that very small segment has a slope that is almost equal to the slope of the tangent at that specific point, and the slope is in fact f prime of a. So the instantaneous rate of change would be as if you're looking for an average rate of change, but with a very infinitely small increment. Some people actually look at it as if it's defined by a vector, by the tangent vector to the curve at that specific point. Because as you can see, the tangent vector at x equals to a has a direction that is defined by the derivative. So you'd really see it as a direction vector of the tangent at that specific point. So that the instantaneous rate of change is really defined by the length of that tangent vector and the direction of that tangent vector as well. So the direction that defines the slope and in which way my model is directed, whether it's positive or negative, and the magnitude of that vector would be defined or would be defining how large my change is or how small my change is. That is defined by the magnitude of that tangent vector. So the instantaneous rate of change would be more or less studying how the curve is oriented and how is it really changing my model as I move from one instant to another one. So over here, going back to our exercise on modeling temperature. So over here, we need to find the average rate of change in temperature during the first 18 days of the month. So during the first 18 days, that's starting from day 1 until the 18th day. So this is an average rate of change. It's being calculated over a period of time. So for part A, that is the temperature on the 18th day minus t of 0. T of 0 for n equals to 0, since n is the number of days that follows the beginning of the month. So over here, during the first 18 days, that's in fact between the beginning of the month for n equals to 0 and the 18th day for n equals to 18. So t of 18 minus t of 0 over 18 minus 0, calculating that would give 0.0297, and that's degrees Celsius a day. So the average rate of change would give the average change per day during that specific period. Now in part B, we are asked to determine the derivative of t. So let me just rewrite the expression. That's 18 plus 12 n e to the n over 3. That's it, right? Yes. And I need to find the derivative here. So I start by differentiating each term. Now the derivative of 18 is 0, being a constant. However, over here I do have a product. This is in the form u times v. So the derivative would be u prime v plus v prime u. So it's good to revisit the previous lessons on derivatives where we tackled the product rule of derivatives, in addition to the lesson on derivatives of exponential function. If you're not really sure how to differentiate such a function, it's good to revisit the other lessons. So u prime v plus v prime u, so that would in fact b. So the derivative of 12n is 12 times v, which is e to the n over 3, plus v prime times u. So it's u times the derivative, so u is 12n, times the derivative of e to the negative n over 3, which is in this case is negative 1/3 e to the negative n over 3. Now simplifying that, 12 over negative 3, that's a negative 4n e to the negative n over 3. So that is our derivative function for the temperature model. Now in part C, we need to find the exact value of the instantaneous rate of change in temperature on day 18. Remember, instantaneous rates of change, as discussed before, they do happen at a specific instant. However, average rate of change happen over a period of time. So the instantaneous rate of change here, as discussed a couple of minutes ago, is in fact represented by the derivative at n equals to 18. So replacing here n by 18, that would give me negative 0.149. Evaluating that on your calculator, that's degrees Celsius a day. However, the 0.149 does really give me the amount by which the temperature is changing over that day, and the sign here being negative implies a decrease in temperature. So the sign would actually represent the decrease or increase in temperature, while the absolute value of that derivative would give me the amount of change during that day, during that specific day.